Hi, welcome back to Aristothink. Today I'm going to show you a problem about friction and acceleration. I have released a previous video about a rocket and different accelerations on this rocket and how to deal with those accelerations. If you haven't seen, consider it worth it seeing it. Somewhere above there you have the link. Now, this problem I'm going to divide into two parts. The first is the train moving at 8 meters per second squared. On the second part of the video is the same train but now moving at only 3 meters per second squared. Inside this train there is this box, and this box is going to move or not depending on how fast the train accelerates. Well, if it does move, there are 10 meters to move, and the back is the limit, and if it moves, it's going to go to the back with this final speeds, VR. R is for relative speed, because I want to know the speed that this guy is looking. You see, I don't want to know the outside. The relative speed is for someone inside the train. So imagine you are this person, you are just looking at the box like this. Well, you are just looking at this box. And if the box moves, it's going to take some time until the back of the train, and that is going to hit with some speed. I want to know this. As simple as this. Now, usually we love to use friction and put friction force and write newtons and so on. Well, on this problem, I'm going to avoid as much as possible to deal with newtons. I don't want to know about newtons. Eventually, I will have to write the second law, which is F equals ma, but I want to solve this problem, think about acceleration, not about newtons. So, let's start the problem. On the first part, this is the acceleration. If the train, but imagine at first there is no friction. Imagine there is nothing there. So if the train moves, the block stays because there is no friction. So the block, the object that is moving is the train, is not the object. The object will only move if there is friction. If there is no friction, if the train moves, the block stays put. But think with me. This is the block. So, if the train moves at this rate, so wouldn't you agree with me that the block for someone inside the train is moving at this rate, same rate? Of course. For someone inside the train, if there is no friction, of course, this person is tied to the train. What doesn't have any friction? Imagine they put butter and oil in here, and so as the train moves, the block goes back. The block is going to move with this acceleration for this person. Now, this is without friction, of course. So it's safe to say that the train imposes this acceleration to the block. This is the first part. But of course, in reality, we do have friction. I put the coefficient of friction here. We do have friction. So, if the train goes forwards, the block is going to try to go backwards. If it goes backwards, the friction is always against the movement. So friction is going to be in this direction. So we would happily write friction force in here. But I don't want to write friction force today. I told you. Instead of writing the friction force, I want to write the acceleration due to friction, because I want to solve it only based on acceleration. So, if there is friction, there is acceleration. Why? Because friction is ma, so there is this a is going to be the acceleration due to friction. So, I'm not going to write friction force, but I'm going to write this is the acceleration, this F is friction. This is the acceleration due to friction. And I want to know what is it. So, on this block, there is going to act two forces. There are going to act two forces. two accelerations, 8 due to the train and AF due to the friction. They're going to fight each other. And on the previous video where I talked about it, we just have to subtract and that's it, just like normal forces. Our first job here is to see what is the maximum acceleration that friction can impose to this block. There is a limit, you know. This is the charge, this is the friction, it goes like this, drops like this. This maximum is mu static times normal. Then, once it reaches the maximum and it starts movement, this is the imminence of movement, this part, then the friction stops, the friction reduces once movement starts, and mu kinetic times normal. So, for these parts we use, for these exactly points we use mu static, and for these parts we use mu kinetic, the dynamic coefficient. Okay, that being said, I want to know the maximum acceleration that friction can have. So let's start. So first part, what is the maximum acceleration due to friction? Well, we know that the friction force is nothing else than mu. I'm going to put a little bit in here. It's going to be mu static times mg. Mu m. This is the friction force, of course. This is equal to mg. Ma friction. This is the acceleration due to friction. I cancel this. So I laid to this final. Acceleration caused by the friction is mu s, which is 0.5, times acceleration of gravity. So acceleration due to friction, maximum 4.9 meter second square. So this is the maximum acceleration that friction can have on this block. 4.9 meter second squared. What does that mean? Well, that means that while the train tries to send the block back at this rate, friction is going to say, hey, stop it. I'm not going to let you do everything. I'm going to fight against. If the train wants to pull the block at 8 meters per second square to the back, friction is going to say, I can do my job as well. So I'm going to fight against with this acceleration. So at the end, this is what we have. We have this block. The train is trying to impose this acceleration to the block. But the friction is fighting back with this acceleration. So what's going to happen? Well, at the end, what can you do here? So the block is going to move. Only this. We cannot say anything else. Okay. The block is going to move. Why? Because clearly 8 is bigger than this. The train is much stronger than what the friction can hold. So sliding is going to occur. Now that sliding is going to occur, we go to the dynamic part of the movements. And that changes a lot because everything we did was using mu s. But since now we said that now the block is going to move, this is considering that the friction would hold everything. It's not going to happen. So movement is going to occur. So we cannot work with this part anymore. We have to use this coefficient. It's the movement coefficient. Now that we know that friction is not going to avoid the movement of the block, So we have to consider now the actual acceleration due to friction. Isn't it the same? No, it's not the same. Because now look, is mu kinetic times mg equals to the mass of the object times the acceleration. This is one acceleration. This is the static acceleration. I said, how come it's static if there is movement? You see, this you have to imagine things. In physics, you have to imagine. It's the maximum acceleration that the friction would impose. This is not movement. So we cancel this one. Now, acceleration due to friction, considering now movements, kinetic, so 0.3 times gravity. Now, this is the static version, and now this is the acceleration of the friction due to the kinetic version. This is the movement itself. Now, once we do this, well, we got 2.94 meter per second squared. Now, this is what we're actually going to use in the problem. Now we have this situation. This is the block. This is movement. This is not movement. We were just studying if movement would occur, and it will occur. Now that we know that's going to occur, this is the acceleration that the train imposes, 8 meters per second squared. And now this is the movement acceleration due to friction, 2.94 meter second squared. Now, just like we saw on the rocket video, if you didn't watch, please consider watching this video. So let me try to be in a better situation here so you can see everything. So now it's easy. So what's going to be the actual acceleration of the block? The actual acceleration is going to be, this is the vector, so it's going to be the 8 minus 2.94. This is against, can you see what's going on? So the train is trying to push the block with 8 in this direction. But friction, while the block is moving, while there is movement on the block, so imagine the block moving. The train is trying to push with 8. But while the block is moving, friction is trying to hold back. It's losing the battle, but it does impose some action. So here, it does impose some action. So while the train is pulling with this rate, the block backwards, friction is losing the battle, but it is still applying some force, you see? And this force represents this acceleration. So the train is not alone. The train is doing this, but the friction is trying to reduce this acceleration by this amount. So the final acceleration of the block is going to be 5.06 meter per second squared. Perfect. So this is actually, this is the acceleration of the block seen by this person. You see, this person is going to see the block moving at this rate inside the train. Now, well, movement is going to occur. This is acceleration of the block. So what you're going to do now? Well, let's find what first. The final speeds. Let's find the final speeds. So part 3. Now, part 3. Well, we can use Torricelli here, right? V squared equal V0 squared plus 2AD. Ring the bell. So, final speeds, so it's going to be V prime squared, V0 squared plus 2 times acceleration times the distance. Well, let's try to hold space as much as possible. V0 is 0 because it starts from rest. Now 2 times acceleration. This is the acceleration. 5.06. The distance, 10 meters. That is, after 10 meters, it hits the wall. That's what I want to know. So if you work out the numbers, you're going to see that V prime is going to be 10.1 meter per second. So this is one answer. This is VR. Now, once we know the final speed, we can just use a simple kinematic equation to get the time. Number 4 and last. To get the time, well, we use the speed, right? V equals V0 plus AT. It works. So, final speed is going to be the initial speed plus acceleration times the time. So, this is 0, clearly. So the time is going to be V prime divided by the acceleration. If you so T equals V prime is 10.1. Acceleration is this. So that means that the time that the box is going to take is going to be 1.99 seconds. Okay, part 1 of the problem is done. This is one answer. This is the other answer. This is not the answer, just something in between. So you see, so this is part 1 of the problem. Now let's solve the second part of the problem. Now things are much more easy because most of the work is done. We know movement is going to occur, but this is for the train at 8 meters per second square. What about the train at 3, less than half the acceleration? Well, we have to do everything over again, but not everything over. Most of the math is already here. So first we have to see, is movement going to occur? Well, we have to think for ourselves. Let's use this information first. Well, let's consider the first case. What is the maximum acceleration? So this is 0.1. So we know that the train is pushing with this rate the block. We know that the friction force can impose this acceleration. Oops, but now it's not 8 anymore, is it? Be careful. It's 3 now. It's only 3. You see? It's only 3. So, solely due to the train, the acceleration imposed by the train on the block is 3 meters per second square into the back, pushing backwards. Of course, against that movement, if the block is going to go into this direction with this acceleration by looking at this guy here, this guy is going to see this acceleration. Imagine there is no friction. If there is no friction, the train accelerates. So if this guy is holding on the train, so the block is going to slide at this rate. But there is friction, and friction is going to impose a maximum acceleration of, so acceleration due to friction is going to be, we saw this. All we have to do is to put friction force equals ma. Cancel mass, static 0.5, g. This. So the maximum acceleration that the block can offer is 4.9 meter per second squared. Now, totally different situation. Look, the train applies this to the block 3. But the friction force say, haha, now it's my turn, because now I win. Because this poor train can offer this acceleration backwards. Haha, I'm much stronger. I can offer almost double as much. So, clearly, friction wins. Now, friction wins. Why? Because friction can upstand an acceleration up to almost 5. So the train can accelerate at 3, 3.5, 4, 4.5, 4.8, even 4.9. Up to 4.9, friction is going to be strong enough to cancel this acceleration. Can you see? So friction is going to win. So what's going to happen? So no movement. So we know that v prime relative is going to be 0 and time not applied. Not applied. Fine, there is no movement. But now, on this case, I want to know what's going to be the value of the friction. It's not right, but I want to know what's going to be the friction force in here. There is going to be a friction. Is friction going to be the maximum friction? No way. No way. It's not going to be the maximum friction. Why? Because friction, let me explain back better. Friction is not going to be maximum. Why? Because the train does not have this maximum acceleration. So what's going to happen? Let's put it this way. So this is the block. So the block wants to go in this direction. Okay, with some force. Now let's put force. I think it's better to explain. Force of the train. But the friction, force of friction, and force T for train, okay? This is a T. So the train is trying to push the block backwards with this force, as seen from this person. But on the other side, there is friction trying to avoid that. Clearly, we saw that friction is much bigger than the force imposed by the train. So we are in this situation. We remember the charge. This is the maximum friction. Maximum friction. We are something like this. We are in here. So this is the force of the train. And this is exactly the friction force. F, friction force. And since this is 45 degrees, so I can say that F of the train equals F friction. So I can say that the friction force is going to be mass times acceleration. Mass is 5 kilograms and acceleration is the acceleration of the train. If I would draw, I told you I want to write everything in terms of acceleration. So if I would draw the block in here, so this is the acceleration of the train. The block is not going to move. If the block is not going to move, hey computer, please don't stop. If the block is not going to move, so it means that friction is applying the exact same acceleration on the other side. Does it make sense to you? Again, if the block is not moving, we saw this, the block is not moving because friction is much stronger than the acceleration of the train. So the friction can give almost 5 meters per second square, while the train is only pushing at 3. So the friction can go much further holding this block. So the block's not moving. Come on! If the train is trying to pull the block with 3 meters per second squared, so friction is going to do the opposite. 3 there, 3 here. You see? To cancel. So the block doesn't move. There is no acceleration. You see? There is no net acceleration. 3 to the train, 3 to the friction. So that's it. So the friction force is going to be mass of the block times the acceleration due to friction. And the acceleration due to friction, it is exactly acceleration of the train. So it matches. It cancels out, I would say. So this is 15 newtons. And that is what I wanted to discuss with you today. Okay, it's a little bit bigger this video, but you see, I'm trying to discuss important situations here. So in this video, what is important is this. Well, we have to understand that not always friction is going to be maximum. If there is movement, you work with maximum friction. But please, if it's moving, you have to use this. But if friction is not at its most in here, then it means that friction can be any value from 0 up to mu s n. Remember, this value is mu static times normal. If there is movement, then friction is going to be exactly mu k n. Perfect. Always, never changes. But if friction, and sometimes exercises, does not force friction to its maximum value, if it's not, friction can be any value up from 0 up to this point. Which value is going to be? There is no formula to get it, to find this. You just have to balance forces. On this case, the train gives this acceleration. So if everything must be balanced because nothing is moving, so friction has this acceleration. Acceleration due to friction is 3. To cancel out the train acceleration. Mass is 5. So friction is this. So you see, when, this is very important, the most important part of the video. If friction is not at its best, its maximum, so how to find friction? Balance forces, balance the accelerations, wherever. There is no movement. How can you do to balance things? This is going to be the value of the friction force. Well, thank you very much for watching. If you stayed the whole video, thank you even further. Very, very glad you did. Now, time to ask you some things. If you enjoy this video, please give a like. It's important to me and most of all to other people, because every time you give a like, you are saying to YouTube, please tell other people that this video is worthwhile, is worth seeing it. So please, if it was interesting to you, please give a like. It's very important. It's not that I'm begging, it's not anything like this, but it is important because without a like, YouTube will consider this video is not worth it to be watched. If it was worth it to you, very likely it's going to be worth it for other thousands of people. So please give it a like. And if you think it's interesting, the way I speak in here, the way I talk, the way I discuss things, please consider subscribing. Every time I'm going to try to make this video, my videos better and better, giving more interesting and challenging situations. And every time I do those videos, I always try to teach something basic as well, because not necessarily you that are watching are a master in physics. Very likely you are just watching just for curiosity, and I want to give everything to everybody that is watching. So please, if you already know most of the things I said, please have patience and learn what you don't. Thank you very much. It was a pleasure to have you here. Thank you very much, and I see you next time. Bye bye.